everybody. I'm Arthur Amorin, and welcome to the Secure Compilation Theory section of PriSC. Our first speaker is Matis Cruz, who's going to tell us about composing secure compilers.
Thank you. So yeah, hi, I'm Matis Cruz, and I represent a collection of preliminary results of joint work with Marco Patrignani on composing secure compilers. So from a programmer's perspective, compilers are black boxes that take a program written in a source language blue S and emit a program now written in a target language red T that morally should behave the same as the original blue program. However, in practice, these black boxes actually consist of many smaller boxes. They might even take in multiple input languages and emit multiple output languages. Take OCaml as an example. It takes in ordinary OCaml code or OCaml bytecode, a custom assembly-like language for their virtual machine, and transforms the abstract syntax to an intermediate representation, which they call lambda form. Now, this lowering process of transforming the blue OCaml code to the yellow intermediate lambda form can be viewed from an abstract perspective as a compiler, aka this box at the very beginning. So-called compilation passes that perform source code transformations are applied on the IR. That is, they have the same input and output language. So in this case, lambda form again. Having applied a suitable number of optimizations, the IR is lowered even further to emit either x86 or other flavors of assembly or OCaml bytecode again. So as you can see, practical compilers typically consist of multiple smaller ones, and what we now want to discuss is how formal guarantees of these smaller compilers propagate through the pipeline, and let us make statements about the big compiler as a whole. Before diving into those details, we need to set up some formal preliminaries and what we consider for a criteria. We consider sets of hyperproperties that we call classes. Note that by lifting properties, classes may intuitively also contain ordinary properties, but through the talk, I'll be referring to elements of classes as properties, regardless of their actual mathematical structure, simply because the term hyperproperty is a bit of a mouthful and the distinction matters only for the details anyways. But nevertheless, if important, I will make sure to distinct between hyperproperties and properties. Also, whenever you see text that is surrounded by such contours as depicted here on the slide, the text shall be interpreted as the name of the set the contour shall abstractly describe. It also doesn't really matter whether you see dashed lines or strike through lines. However, dashed lines are an indication that what you are looking at is supposed to be a class, and the other stuff are supposed to be properties or hyperproperties. Okay, so here, C is the name of the class, which contains properties now x greater 0, non-interference, and non-termination. Using classes, we now work towards defining robust compilers. To do so, we first develop the notion of satisfaction, which can be formulated for classes and individual properties. When formulated for properties, we would write P turnstile pi instead of P turnstile C. Let's look at how it is defined for classes that, of course, may contain numerous properties pi. During the talk, however, I'll just highlight one element, but the quantification is always a for all one. So for satisfaction, any property pi in class C shall contain the behavior of a given program P. Now, extending the notion of satisfaction to robust satisfaction allows us to include an attacker model. So here, instead of looking at the behavior of a given program P, we look at its behavior when linked to an arbitrary context, and I will refer to such behaviors later as robust behavior. Linkage in our work is represented with this bow tie and language dependent. That is, to make a concrete example with a single context, we might have a C program here on the right-hand side that calls a function named toLower. Now, a context here on the left-hand side is an implementation of that function toLower. Linking both programs together on the C level shall result in one combined big C program. Now, the role of the attacker lies in the implementation of toLower. Now, using robust satisfaction, we can define the compiler-level property robust compilation. So, given a compiler here from source blue S to target red T, we say it robustly preserves the class C if for all properties pi in that class, given a more or less arbitrary source program blue P, whose robust behavior, however, is in pi, it holds that the robust behavior of compiled P is also in pi. That is, assuming source level robust satisfaction of a pi from class C, target level robust satisfaction must also hold. What is also important is that our work is based on a unified trace model. So all languages share the same traces. Thus, colors here used here for program behaviors are merely an indication what programming language the program with that particular behavior is written in. But anyhow, we are ready to prove our first compositionality result already. So, given two robust compilers that preserve classes C0 and C1 respectively, we now show that their composition, so first running the compiler from blue S to yellow I, then the one from yellow I to red T, preserves the intersection of the classes C0 and C1. First, note that the robust compilation criterion gives us the assumption that the blue source program's behavior lies in all pi's in the intersection of classes C0 and C1. Since pi is an element of the intersection of C0 and C1, it is okay to forget about C1, quote unquote forget, and just focus on the fact that pi is an element of C0. This allows us to apply the fact that the compiler from blue S to yellow I is robust with respect to C0. So one can conclude that the yellow robust behavior of the original blue program is still in all pi's. Now again, let's remind ourselves that all pi's are on the intersection of C0 and C1, so it is fine to switch gears and just focus on the fact that pi is an element of C1. And we did this trick before, but now we can apply the fact that the compiler from yellow I to red T is robust with respect to C1, and we end up with the fact that the red target level version of the blue source level program has a robust behavior that is in all pi's that lie in the intersection of C0 and C1. Now, as an example, take again OCaml, its lambda form and assembly. For classes, pick safety and hypersafety. Since hypersafety is a superset of safety, sequentially composing robust compilers from OCaml to lambda form and from lambda form to assembly yields just safety. Also note the little rooster at the top of this slide. Whenever you see it, this indicates that we have proven in Coq what is depicted on the slide. But now let us talk a bit more about the intersection of security classes. So here you can see the lattice of various robust preservation compiler properties taken out of the Journey Beyond paper published by Abad et al. In 2018. Sequentially composing, for example, a compiler fulfilling robust hyperproperty preservation with another one that just fulfills robust trace property preservation means that the resulting compiler fulfills their least upper bound. So here, just robust trace property preservation. As a rule of thumb, always use the lower thing in this diagram. Now, the sequential composition lemma has an interesting consequence for robust compilation passes, which are compilers that have the same input and output language. So given that the behavior of a source program lies in all properties that are contained in the intersection of C0 and C1, by sequential composition, we already know that we get a robust compiler. That is, running pass 0 before pass 1, while pass 0 preserves C0 and pass 1 preserves C1, gets us the intersection of C0 and C1. However, the cool thing is that this also works in the other direction. So first running pass 1 and then pass 0, and this little corollary gives compiler writers the formal guarantee that it is acceptable to swap around robust optimization passes, which is important since the order of optimizations influences the quality of the emitted code. As an example, take common subexpression elimination for pass 0 and copy propagation for pass 1. Assuming they have been proven robust, it doesn't matter from a property preservation perspective in which order we run them. However, consider the program C equals B, X equals A plus B, and Y equals A plus C. First running common subexpression elimination doesn't give us anything, but then running copy propagation only gets us the fact that X equals A plus B and Y equals A plus B. But first running copy propagation and then comment subexpression elimination enables us to factor out the A plus B and thus assign X and Y to the same temporary. So we've optimized the code even further and thus enabled the resulting binary to run potentially faster. Now you might remember the motivational slide, and right now we have only covered some aspects of the middle part. But on the left-hand side, you can see there's another kind of composition, which we refer to as simply upper composition. We will now prove that the upper composition behaves similar to sequential composition. So given two compilers from blue S to red T and pink O to red T, which are robust with respect to C0 and C1 respectively, we are given some program P and check whether it is written in the language blue S. Applying the fact that the compiler from blue S to red T is robust with respect to C0 gives us that the compiled source behavior is in all properties pi that lie in C0. Now, similarly, if the original program is not written in blue S but in pink O, we can apply the fact that the compiler from pink O to red T is robust with respect to C1. Now, remembering the definition of robust compilation of the previously discussed proof of the sequential composition lemma, we start by assuming that the behavior of some program lies in all pi's that are part of the intersection of C0 and C1. Thus, we know that the upper composition of compilers from blue S to red T and pink O to red T is robustly preserving the intersection of classes C0 and C1, since we can simply take the lower or the upper path in this diagram in a similar manner as with the sequential composition lemma. Now, to emphasize another practical example of this composition that is not just OCaml plus OCaml bytecode, take C and Fortran. The GNU compiler collection happily accepts both and compiles them to assembly. Now that we have seen a selection of theoretical results with regards to preserving a property that is already present in the source program, we want to additionally investigate what if, for example, the source language's type system is not strong enough to guarantee that a class of properties trivially holds. So suppose we have some program behavior in an intermediate level yellow language I and compile it to a target level program whose robust behavior is in all properties pi that are part of some class C. Now, this is different from before. Before, we knew the behavior was an element of a pi of some C and did compile the program from, for example, blue S to red T, and thus get that the behavior of the resulting red program also is in pi of C. So what we want from this small compiler from I to T is to essentially zap a target level behavior into a pi of class C, regardless of the original intermediate program's behavior. Like, we might even know something about the yellow behavior, namely that it lies in some pi 0 or pi 1 or whatnot. This all doesn't matter. The compiler from yellow I to red T is an enforcement of the class of properties C. Now, even though we use the terminology classes, it might be a bit misleading for enforcements. So take safety as an example. Now, as a reminder, compilers may robustly preserve safety properties, but what about enforcement? We believe enforcements only work on small classes, since one doesn't get any useful assumptions here. Like, proving this for all safety properties is quite a daunting task, right? Now take memory safety as an example. Here one can think of a transformation that enforces it, which is backed up by the huge number of published academic papers on that. In summary, we propose the use of enforcements for individual properties. To make my point really clear, compare the enforcement with the robust compilation criterion. So here on the left, the enforcement, we always get that the behavior of the target program is in a pi that is in some class C, regardless of the source, or in this graphic, the intermediate behavior. Now on the right, robust compilation, we get this fact that the behavior is in a pi that is in C, but only given that the source program already is. So robust compilation constrains the source behavior suitably, while enforcements literally enforce certain behaviors. Now, such enforcements have, especially in the context of preservation of, for example, security properties, an issue. So suppose we have the property C0, no out-of-bounds accesses, and C1, no spectral V1 attacks. On the left-hand side, you can see a C++-like program that allocates an array of 42 integers and prints out the content of the integer in the array at the ith position, where I is an unknown unsigned integer. So we do not know whether C0 holds, since we do not know the value of I. But we know that the program is not violating C1, thus the speculative leaks. Of course, I'm ignoring the details of the actual implementation of the operator new and the function putC, but let's just ignore that for now and view this as given. As mentioned before, a great body of research has proposed such transformations. Now say we have an enforcement that translates this program and enforces that no out-of-bounds accesses happen. Now, as mentioned before, a great body of research has proposed such transformations for the sake of our overall storytelling. However, let's say we do it in a simplified style as presented in Softbound, published by Nagarakate et al. In 2009. So by inserting a branch which checks whether I is smaller 42 and only then performs the access. Even though this enforces that no out-of-bounds accesses happen, we now have violated C1, since there is a speculative leak now. In order to fix this, because we want the final program to both robustly satisfy C0 and C1, we add the requirement that the source code instrumentation, namely the compiler from yellow I to yellow I, is also robust with respect to C1. Thus, our transformation cannot trivially insert ifs before each load, but, for example, needs to insert an additional elfence instruction in order to prevent that the secrets are leaked on the cache. We'll now use this arrow notation here for so-called secure enforcements, which preserve the class that is written above the arrow and enforce the class that the arrow points to. Thus, a secure enforcement is both a preservation and an enforcement. Let's see how robust compilation interacts with secure enforcements. So given some compiler from blue S to yellow I that is robust with respect to class C0, plugging the output of it sequentially into a secure enforcement of C1 that preserves C0 results in the preservation of the union of C0 and C1. Now, that is not too difficult to see. The one side, C0, comes by the fact that the compiler from blue S to yellow I preserves C0 and the other compiler from yellow I to red T, too. The other side, C1, doesn't involve the compiler from blue S to yellow I at all. We simply apply the fact that the secure enforcement from yellow I to red T is in fact an enforcement of C1. Curiously enough, if we switch the order of the secure enforcement and the robust compiler, things might not work out as you expect. But for now, let's say our secure enforcement is, again, a softbound, and our classes are for C0 all safety properties, and C1 is a singleton class which contains the property of spatial memory safety, which softbound tries to enforce. Here, the diagram works out, and the union goes away, since we know that C0 is a superset of C1. However, if C0 is not a superset, for example, now take temporal memory safety, the robust compiler that preserves C1 might annihilate what softbound has done. It might, as an example, use an auxiliary array and, while preserving temporal memory safety, perform accesses to this auxiliary array that are out of bounds. So we have seen that secure enforcements can give us the union. However, the union is not necessarily that interesting if you union all safety properties with some hand-picked safety property. So consider memory safety, which may be split into temporal and spatial memory safety. To emphasize a crucial point, let's first consider the sequential composition such that the resulting compiler is a secure enforcement and not just robust. Unfolding the definition, we get as an assumption that some source program's robust behavior lies in temporal memory safety. Note that the union does not come into play here at all. The secure enforcement consists of an enforcement of spatial memory safety and a preservation of temporal memory safety. And the preservation is the only thing that gives us an assumption. The compiler from blue S to yellow I preserves the property, and the compiler from yellow I to red T not only preserves the property, it also enforces spatial memory safety. That's why we know that the target program's behavior, given any source program plugged into the sequential composition of the compilers, lies in both temporal memory safety and spatial memory safety. Now, comparing this state of affairs with the preservation of the union of these two classes, unfolding the definition of robust compilers, we get as an assumption that the behavior of a given blue program is in temporal memory safety or in spatial memory safety. And you know the drill by now. Applying the robust compilation of blue S to yellow I, we preserve the property temporal memory safety. However, there's nothing we can say, at least from this abstract perspective, about spatial memory safety for the intermediate level. The applied compiler might preserve it, but it might also do something funky while preserving temporal memory safety. So the only thing we really know at this point is that the yellow target behavior is temporal memory safe. But applying the secure enforcement in a similar style to before, we get to both preserve temporal memory safety and enforce spatial memory safety. Thus end up with the situation that the behavior of the target program is in all properties that are contained in the union of temporal memory safety and spatial memory safety. That means we have essentially two options. The first being, given a source is in temporal memory safety, we know in the end that it is in temporal memory safety and spatial memory safety. So there would be an intersection here again and not the union. However, the composed secure enforcement is even stronger in a sense, because we also have a second option. Given an arbitrary source where we know nothing about, so this left branch here falls completely away, and we just use this secure enforcement, the least thing that we know is at least that it is spatial memory safe, due to the fact that it is an enforcement. The key difference is that both options work here, but for preservation, we know nothing about programs that do not satisfy either temporal memory safety or spatial memory safety. There are two takeaways here. First, as noted now, robust compilation is somewhat weaker than secure enforcement. Second, compilers in the pipeline might influence the behavior of an intermediate level program in such a way that certain properties we want to have from the outside do not necessarily hold anymore. So here, spatial memory safety. Nevertheless, having an enforcement in the pipeline, we can fix up things and get to both preserve spatial memory safety and temporal memory safety. Now, this basically concludes my talk, and in the future, we want to discover and prove more lemmas with regards to existing compositions that we have presented, but also want to investigate other composition operators altogether, such as lower composition, where you have two compilers that emit different output languages. Furthermore, we will apply our results to a series of toy languages. And that's it from our side. Thanks for listening, and let us know if you have any questions.
All right, thanks, Mathis. Let's see if we have any questions from the audience. Do we have any questions on the online section? Okay. I do have a question about clarification. You mentioned in that previous slide that something about preserving both temporal and spatial memory safety. I was a little bit confused because there's a union symbol there. And at some point, you did talk about this union wanting to be an intersection, but I didn't quite get if you want to preserve both or either. So could you clarify that?
Sure. The point that I'm trying to make here is basically that the robust compilation, as we've defined it, is in a sense weak with regards to the union, because the union only gives you either the fact that a given program, a given source program, is in temporal memory safety or in spatial memory safety, or of course in both. And in the case when it is in both, then we again have the intersection case where we know that it is both in temporal memory safety and in spatial memory safety, also in the target. But if we only know that it is spatial memory safe or temporal memory safe, then it gets a bit more hairy. Compared to the secure enforcement, where we can always conclude that the resulting target program is spatial memory safe, for example.
Okay, I see. Thank you. We do have a question here from the audience. Let's hear from Vadim.
So you worked algebra of this kind of algebra enforcement or preservations. Have you thought about the system as a whole? And you have this multiple passes or compilers, some enforcing, some preserving, and if there is an optimal combination of them to preserve or enforce maximum number of properties, and a way to arrange these passes in the most optimal way?
That's a good question, and actually that's still future work. However, the intuition is that you always preserve the lower bound in this lattice as presented by Abad et al., which I will go back to right now. Excuse the flickering slides. Let me see where it was. Yep. Right. So you always get to the lower part. Given two compilers, one might be here, the other one might be here, or for the sake of the storytelling here, then you always get to the one that is lower in this lattice. And of course, depending on how you choose to compose your compilers, if one compiler in your chain is very low down here, then you probably want to put it in the end, because then you have stronger guarantees for your intermediate level languages.
Thank you. Thank you.
Yeah, we do have a question from the online audience. Could we project that, please? The question is, does your formalism assume that the behaviors at different levels are comparable? When we consider sequential.
Could you explain what you mean by comparable? Because we use the same trace model, so hey.
I think that was my question. Were you using the same trace model at each level? So in particular, we encountered some difficulties where if you imagined there were events that you could observe at one level of abstraction and they were erased, you could reason about the lower level compiler preserving the things that it saw. But when you tried to do the composition, you sort of couldn't say anything about the behaviors that were erased. And so we came up with some really gross conditions for what what you needed to have true about the behaviors at each level. And I was curious if you had thought about that or had some insights that we didn't.
Unfortunately not. This is future work. But we do want to investigate that, definitely.